All right. So, good morning, everyone. Let's just quickly uh, revise whatever we did last week. We said statistical inference is more to do with sample data, right? Doesn't have much relevance if we had the whole concrete data available to us, right? And basically, we want to quantify our certainty, and which arises based mainly from incomplete data or bad data, right? So these are the two main things. And then statistic is a singular measure, right? A numeric computation, and the outcome of any such experiment where the data is not fully available to us is that it's a random variable, right? And we apply some deterministic processes, for example mean, median, etc., on these random variables, and they produce further more random variables, okay, which have a probability. When you say randomness, there's a probability involved, okay. and and then we said, okay, fine. So in probability, outcomes of an experiment are all the possible outcomes. For example, if you roll a die, then the outcomes are 1 2 3 4 5 6, right? So probability of particular outcome is the number of ways outcome can occur divided by the number of ways for all the possible outcomes, okay. And say if we say the probability of an event, so the probability of an event has to lie strictly between 0 and 1, because if the probability is 0, that means the event is impossible. On the other hand, if there's a certain event, then the probability is 1, okay. And we know this, right? So the probability of a dot b is probability of a into probability b, where if both the events are independent, right? And say for example, rolling the die twice, right? So what are the possible outcomes if we roll the die, two dice, right? So the outcomes are 36 and not 11. 11 are the uh, outputs. So 11 are the outcomes of or the different you can say values that are coming out of those outcomes, right? So we have to be clear about how outcome is different from the outputs, okay. And then there's a simple Venn diagram equation where I say p of an event a union b is nothing but probability of an event a plus probability of an event b minus the probability of the intersection of the two. And we saw this with an example, okay. uh, and and then we said, okay, we have random variables, and a random variable is a numerical outcome of an experiment. So this is key here, it's a numerical outcome. Let's say if I'm tossing a coin, right, the outcome is heads or tails, so it's not numerical. I convert it into numerical by assigning a value to heads and a value to tails, right? And then so random variables can be of two types. One is discrete, another is continuous. So in discrete, the possibilities are countable. For example, rolling the die, right, you can count the possibilities, whereas in continuous, it can be any value, it can be any real number. Hmm? So so that is the key difference. Now there are certain cases where the measurement can only be discrete, but because of the ways that you can measure, right, the precision of measuring, that does not mean the values are discrete. We took the example of measuring the height of people, right? So we measure the height of people using some kind of instruments. Say we say the height is 6 feet 7.2 inches or 3 inches, so that does not mean that uh, the values are discrete. It's just that our capturing of the values is discrete, whereas the data will still be treated as continuous. Okay, so now the key other concept here is something called a probability mass function and a probability density function. So what's the definition of a probability mass function? It basically gives the probability that a discrete random variable is exactly equal to some value, right? So we saw an example yesterday. We said, okay, fine. If I was tossing a coin, all right. So I'm tossing a coin, then say these are the values of that I can show up. So 2, 3, 4, 5, 6. Yeah. And so in this case, all the probabilities will be 1 by 6, right? Sorry, not tossing a coin, throwing a die, right? So this is going to be my probability mass function for the roll of a die. You guys can hear me? Everything is audible and clear? The screen is also clear? Yeah. Okay. Yeah. So this is going to be my probability mass function. On the other hand, now probability mass function doesn't make sense for continuous variables, right? Because for continuous variable, there is the probability of one particular value happening is what? Tell me, what's the probability of one particular value happening, exactly one particular value happening? No. So let's say it's a continuous, uh, let's say height, right? I want to plot the height of the human beings in on the planet. All right. Now that height, what will the probability of the height be, right? Of at any one particular value. Let us say exactly 6 feet, right? Exactly 6 feet. That value will be too small, right? Because we're saying continuous variable. The value will be very minuscule. So when I say exactly 6 feet, I mean to say 6.00000000000 and so on. So, or even if I was to measure it till 6.001, even then the probability, because it becomes discrete, then I can get some values. But otherwise, as such, it is almost zero. So on a real line, right? If I look at real numbers, let me just explain this concept to you. Is this clear or not? That the actually it will be zero. The probability on the real line of any one particular instance happening is zero. It tends to zero. It's not zero, it tends to zero. Is this point clear? Yeah, right. So 1 by total, roughly, Utkarsh said 1 by total. Roughly, you can say, assuming that everything is evenly distributed, right? Then it can be 1 by total. And but that 1 by total, let's say even for the height, okay? Uh, let's say the height ranges between uh, 3 feet and 9 feet, all right, for the humans. So in that 6 feet bandwidth, the population of 7 billion is there, right? And assume that that is evenly distributed, so you will get a very minuscule small number, right? So it doesn't make sense for me to do a probability mass function, okay, for a continuous variable. So what do I have? I say, okay, what I can actually tell for a continuous variable is not the probability at a particular instance, but the probability uh, between two values. All right, so I can say what is the probability uh, of height being between 6.15 inches and 6.157 inches, right? So when I specifically mention two values, then I can take the values, right? So let us look at this a little more. Do you want me to show this to you guys? The probability density function, so that you understand it better. Okay, so uh, so what I'm saying is, so we had the probability mass function. All right, fair enough. This is discrete values, 1, 2, 3, 4, 5, 6, and so on. But when you're talking about probability density, now there are values everywhere here on the x-axis, right? So I have values throughout, whereas here I have values only at the points, right? So now, effectively, if this was probability, then the probability at each of these points is so minuscule, I can't even plot it. So what do I actually plot? What I plot is the density function, which means I can take two particular values, okay? Let's say this, let me call it x1, and this, and let me call it x2, all right? And let them be close to each other, not very far away. Now, what I can say is that the probability that the x is less than equal to x2 and greater than equal to x1, all right? This I can give provide with some certainty, some value, right? I'd say, uh, let's say some value v, all right? So now this value v I can provide with some certainty. What will this value v be? It will be some height h, let's call it h, all right? Assuming they're very close to each other, all right? So I say some height h, okay? Let's say assuming this is right. So height h into x2 minus x1, all right? So this will give me the probability that the value lies between x1 and x2. Is this clear? So this is how I go on plotting my curve. So I may have another curve on the y-axis, let's say y-axis, okay? So which goes something like this, whatever way it goes, all right? But know that this probability curve is a probability density curve rather than a probability curve. So understand this fine difference between the two. Here I'm taking two different values, and I'm measuring that area, and that area will give me the probability between those two values. Is this fine? Have you understood what is a probability density function compared to a probability mass function? Utkarsh, is it clear? Lavita, Debashri, Raghav, Sarvani, Abhishek. Okay. Hmm. So, all right. So let's move ahead, right? Now, what I can do is, as we see that I can actually take the cumulative density function of a random variable also. All right. So now the cumulative density function can be for both, for discrete or for continuous function. All right. So what is a cumulative density function? It says that the probability such that, so let's say it our function, earlier function was p, right, capital P. Now I'm saying my function is capital F. So the CDF for a small value x is such that the probability of the random variable is less than equal to x. All right, so this is important here. So I'm saying less than equal to x. If that is the scenario, let us plot the CDF here. Let us, so what will be my CDF looking like for the discrete values here? So this was 1 by 6. All right, so this was my this is my probability uh, uh, function for roll of a die. Can you plot the CDF for the same? How will the CDF look like? So it look like, so what function will it look like if I was to plot the CDF for this? Increasing till 1. So it will be a slope. Okay. So Lavita says it will be an increasing value till 1. Okay. First thing is my x-axis will be still the same, 1, 2, 3, 4, 5, and 6. Now increasing, perfect. Yes, it will be increasing, but increasing, but not line. So what will it be, Utkarsh, if it is not a line? Let's come back to our, exactly, right? It will be a step function here. If you look at it, it says probability that x is less than equal to small x. So probability of the die roll being less than equal to 1, right? So probability of the die roll being less than equal to 1, what will be that? 1 by 6, right? So all this while I will have 1 by 6 here. Let's say this is 1 by 6. Fine. Till 1. The moment I hit 1, it will become, it will straight be a jump, straight, and becomes 2 by 6, right? Again a jump, becomes 3 by 6, 4 by 6, 5 by 6, right? 6 by 6, right? So the moment I touch this that becomes 1, right? So it will be a step function. You can see this. Yeah, so this is my CDF for this particular function. Yeah, so now if I was to do the CDF for a probability density function, how would I do that, right? So a CDF for a probability density function is similar kind of things. Okay, it's the same, only thing is it will end up showing up as an integral. All right, so basically it will be the integral of a uh, probability density function. Is this clear? With a lower bound and an upper bound. Okay, so is this clear? The CDF is also clear to you guys? So there's something called a survival function. Survival function is nothing but 1 minus the CDF, right? So the probability that the value is greater than x. Okay, so integral of the PDF will give you the CDF. On the other hand, for discrete values, we saw that we can actually just draw it. Yeah. Okay, now so let's do this. What we will do is we'll define a function. Okay, so I'm defining a function my PDF, all right, such that it is x by 2. All right, and then let's see what I can do. How can I find out the CDF for that? Okay, so let's say my PDF is equal to a function of x such that it is x by 2. All right, so it's just a s- simple sloping line. Okay, now I can use a function called integrate. Okay, but this integrate will actually give me the value. All right, so I use a function called integrate. Now this function integrate has three inputs. First is the name of the function that you have. All right, so in my case it is my PDF. All right, and then what is the lower bound? So let's look at this example. Let's say this is my PDF on the x-axis where the value is x by 2. All right, so tell me, how will the PDF look like? Okay, another important conditions which I had already mentioned in the last class also. The PDF should be such that uh, the integral. So tell me, what will be the one key condition for the PDF? Uh, I've told you that the PDF is basically the area under the curve should be such that uh, it is indicating the probability value between that those two uh, extreme points. So if we know this, what is one strong condition on PDF? Exactly, right? The integral has to be one. It cannot be more than one. Overall, the probability is just one. So if that is the case, let us look at this line, right? I say x by 2. If I have a line which is x by 2 and I say that my lower bound is 0, okay, for this, then what will be my upper bound so that this condition gets satisfied? I had this line called x by 2 as my function, PDF function, but this has to have a lower bound and an upper bound after which the value should become 0, right? In this particular case, not necessarily for all the curves, okay, because in this curve it's a continuously increasing function, right? So what will be my upper bound? 0 to 2, right? So we know this because if I take it as 0 to 2, then the average the area of the triangle becomes 1, right? Similarly, if I was to start off from 1, right, in this case x1, we had solved this last time, becomes under root of 5, right? So if we start off as the lower value as 1, and root of 5 will give me the upper value. Okay, so this is how the PDF seems to be working. Now I'm saying, if I want to integrate, let's say what I want to do is I want to find out the probability such that the value is less than equal to 1.6 for this PDF, where the upper bound and the lower bound is 0 to 2, right? So I can do it mathematically, right? What I need to do is, so I draw a line here and I take the area under the curve, right? So I draw a line here at 1.6. All right, so I say, what is the area of this triangle? So this is 1.6. This will become, so if this is 1, right, uh, so this will be zero point 0.8, right? So 1.6 into zero point 0.8 into half, so that becomes 0.64. So basically this is the probability that I get a value which is less than equal to 1.6. If the probability density function looks something like this, is 64%. Is this clear? Hmm? So I can do the same thing using this integrate function. I say integrate my PDF. Is this part clear to you, that the probability will be 64%? Yeah. Okay, right. So now what I do is I say PDF 0 comma 2 integrate. So for that I get a value of 1, it and also gives an absolute error. Similarly, if I was to do till 1.6, I get 0.64. Correct. So the integrate function of R will straight away measure those values for you, and in this case it's a straightforward PDF function, in the sense it's just a straight line, so not a big deal. But suppose you have functions which are not directly maybe integratable, right? There are functions you can't even directly integrate them, or they're just line curves in some way, uh, or they are curves that you actually can integrate, but it's a little complicated to do that. The integrate function takes care of that for you. Is this clear? So practically speaking, there is an integrate function in Excel, which in R, which allows us this computation. Okay. So for example, if I had a PDF which is x by 2, so what will be my CDF in that case, right? So integrating x by 2, so I get x squared by 4, right? And then I have the lower bound and the upper bound, right? So my lower bound will be 0 and the upper bound becomes 2. And So is this also clear to you? So this was my function initially. The CDF will be value at a point, whereas the PDF is area between two bounds. Hmm? Okay. So, so for example, if I was to find out the median, okay, in the PDF also, where is the 50% value lying? Let's look at the PDF. So 50, what is that value of X? Don't go by the CDF, just look at the PDF part. What is that value of X such that my it's actually a median, or rather I can say that it is the half of middle of the value, right? So how can I uh, calculate that using just the PDF? What will be that value? How do I go about doing it? I can say this is some value X, right? So I want to measure where is this X such that this area is half. I can do that, right? Easily. I can say it'll be 50% of Y. No, no, no. It'll not be 50% of Y. Sarvani. So Sarvani said 50% of Y. 50% of Y will not give me the median. So by the way, this is the only that's the reason why I've asked you this question. Some of you, many of you might end up confusing this as I'm talking about the PDF, not for the CDF. In PDF, yes, it'll be 50% of Y, but for sorry, in CDF it'll be 50% of Y, but for PDF, what will that value be? How can I compute it? I say 50%, so it will not be 50% of Y. It will be some value X here, such that X into Y, which is X by 2, into the area of the triangle, right? Which means half of this should be equal to zero point 0.5, which implies that X is equal to root of 2, right? So even without integrating, Lavita, right? So instead of integrating, if I was to just look at the triangle and measure that value, yeah, so the area has to be 50% of the bigger triangle. It will be at root 2, no? Clear? Now in the case of CDF function, because that has already been accounted for, what I need to do is I just need to take 50% of Y, because straight away I'm getting the probability 50%, right? And when I draw the line down there, I get the answer. In this case, it is x square by 4, right? This is my curve. So I'm saying uh, such that x square by 4 is equal to zero point 0.5, right? Is that coming out to be correct? Mm, right, yeah. So x square by 4 is equal to 0 0.5. Again, I'm getting x is equal to root 2. So same, both ways I'm able to do the same computation, but in the PDF case, it will be little more involved. CDF will take care of it more directly. All right, if I was to do these kind of measurements, for example, what is the median value, what is the 75 percentile value, right, and so on. Okay, so we clearly see the advantage of the CDF over the PDF. So the same thing can be represented as quantiles, I can say, right? Just like we did in the median case, I can say 50 percentile, right? So 50 percentile is nothing but a CDF value of zero point 0.5, right? Or 75 percentile is a value of 0.75. So basically, I'm saying quantile is just like we did last time, as we did it, right? We say f of xv such that v is equal to zero point 0.5 for the median case, right? And then we solved it for ourselves. Is this clear? Okay, let's move to. So we're saying that. So now there are just these two new terms that are used. So one is called the estimator and the other is the estimand, right? So I'm saying my population median. Now this is an actual value, but it's an unknown value, right? So the population median, so the whole population of the planet, there has to be some uh, um average age, let's say today, right? All the people who are living on the planet, there has to be some average age, but to compute it is almost impossible, right? And on the other hand, I have a sample median, right? Now that is the estimator value. So I am estimating the estimand. Okay, so the estimand is the actual value, but it will always be unknown. Okay, but estimator is what I'm using with from my sample data to kind of get closer to my estimand. Okay, so all right, so let's move to conditional probability. Uh, say, let's say, uh, let me ask it as a question. Uh, so what is the probability that when you roll a single die, you get a 3? 1 by 6, right? So the probability that I get a 3 is 1 by 6. Now I tell you this, that I rolled a die, okay, and the numbers are odd numbers. So, right? So whatever I got was an odd number. Having known this fact, what is the probability that you got a 3? Will be, so I have already rolled the die, all right? And I tell you that when I rolled the die, the it actually came out to be an odd number. So now the probability will be straight away 1 by 3, right? Because if it's already an odd number, it'll be 3 5 1 uh, 1 3 or 5, right? So then I'm left with 1 by 3. Now how did, so this is the key thing about conditional probability. I'm saying the probability has changed, right? Earlier it was 1 by 6, now it has become 1 by 3. Why? Because some event has already occurred. So let's assume that there are two events, right? A and B. So B is the event that I got a uh, so the notation is this: probability of A given B, right? So B has already occurred, right? So A is what I need to find out. So the formula is that it will be the intersection of A and B divided by probability of B. All right, and similarly the reverse. I can say the probability of B given A is equal to probability of A intersection B divided by probability of A, right? And this is called the Bayes rule, where I can say probability of B given A is nothing but probability of A given B, and then I replace the A intersection B by the formula here, right? So this is my simple Bayes rule, right? So probability of B given A divided by probability of A given B is equal to probability of B divided by probability of A. Okay, so this looks very simple, and it is very simple. We'll look at a very nice example of this, a useful example of this concept as we move ahead in the class. Yeah. Okay. Now what I'm saying is, what happens is, so straight away we are jumping to the example. Okay. Uh, I'm saying sometimes what happens is that the event does not occur independently. All right. Or event can occur independently, but I do not know the probability of the event occurring independently. I can't measure it. All right. But I can measure the event's probability given some other event has occurred. That is measurable. Have you understood this concept? Right? So then what I can do, if I can measure some other event's probability, all right, and I can measure the probability of, say, I can measure the probability of event B. At the same time, I can measure the probability of event A, knowing that A has occurred or not occurred. Then I can also measure the probability of event A independently. Is this concept clear? Using the Bayes law, right? So in the Bayes rule, if I go back here, right? So basically I can expand this, right? So probability of A intersection B. Do I need to kind of do any expansion and all? Will take much time. All I'm just saying this much simple, right? I'm saying, okay, now tilde is a notation that I'm using, that let's say the B has not occurred, right? So I'm saying probability of A, what are the possibilities? Let's say either B has occurred or B has not occurred. Are you getting this? In our case, the example that we took is the die roll, right? So I say, what is the probability of uh, uh, A given that what is the probability of getting a 3 given that a odd number has been rolled, right? That probability is 1 by 3, right? So I say P of A by B is 1 by 3 into probability of B, that is the rolling of a odd number, that is 1 by 2. So this becomes 1 by 6, whereas A is the probability of rolling 1 by 3, of rolling a 3, so that is 1 by 6. And then what is the probability of uh, getting a 3 if an odd number has not been rolled? 0, right? Because once an even number has been rolled, then you don't get anything, which means, say, so I can say the probability of, so in this scenario it is so that it is exclusive, but normally it is not such a case, right? So is this equation clear to you? I'm saying probability of A given B into probability of B plus probability of A given that B has not occurred into probability of B not occurring gives me the probability of A. Have you understood this simple equation? We will use this to come out with something interesting. All right. Now what I'm saying is, let's say somebody goes to the clinic for an HIV test, all right, and his test comes out positive. So the test says that yes, this person has HIV, all right. Now, what is the actual probability that that person has HIV? Hmm? So now directly there the measure is not there, let's say, right? So the test is conveying positive, or the test may convey that the person does not have HIV. After the test has conveyed that the person doesn't have HIV, what is the probability that he has HIV? So these are the kind of questions that I want to answer, right? Wherein I say, okay, somebody goes for a test, what will be the actual probability of that person having of, or the validity of the text, or rather the efficient, I say accuracy kind of thing for the test, all right. So that is what we will be. So practical usage is what comes in here from the base rule, all right. So let's look at one example wherein I say D is the event that a patient has HIV. So D is that event, all right, the patient has HIV, and positive is the event that the patient tested positive, all right. So they are kind of mutually exclusive as such, if you look at it just directly, though they are actually related, all right. But we are saying D is the event that patient has HIV, plus is the event that the patient has tested positive. So now the probability, let's say this probability is known, probability that the patient tested positive, given that he was an HIV positive, right, he belonged to D. Is this clear? So how this is what the doctors can measure, right? What the doctors can only measure that, okay, if the patients came, they know that this person already has HIV, right? They have done so many tests. After that, they perform their tests. Let's say they devise some test, right? And say they perform these tests on 100 patients whom they know already have HIV. Okay. Out of that, what is the probability that out of those 100 patients, how many will show up in the test as having AIDS, right? Having HIV. Are you clear with the question? Basically, it tells you the accuracy of the test, right? So if it was 100 on 100, that means this value will be 1. But typically that doesn't happen, right? There will be at least one person or maybe some fraction of the people whom the test may say, oh, this person does not have HIV, but the person may actually have HIV, right? So I'm saying the probability of the test being positive, given that the person has HIV, let me call it sensitivity of the test, all right? And similarly, so it's, I can say the person doesn't have HIV, all right, and the test should actually show up negative, right? That's how the test should be. But in reality, the test will not be 100% accurate. Accurate. So what is the accuracy rate? Let me call it as the probability, right? So let the accuracy rate be, say, let's say 0.99 or whatever. Huh? So the probability of showing up that the patient doesn't have HIV, or the negative outcome, given that he doesn't belong to the HIV set, all right, is known as, let's say, specificity. Okay. So once I know this, I also know the probability of the reverse of this, right? So this probability of positive given D is nothing but 1 minus probability of showing up as a negative given D. Is this clear? Similarly, probability of negative outcome given tilde D is nothing but 1 minus probability of positive outcome given tilde D. Is this clear? These two equations are clear to you? Not just mathematically, conceptually. Mathematically, they look simple. Okay. Hmm. Now let's say it's given to us. There are three probabilities that are already given to us. So what is given to us is the sensitivity level and the specificity level. So the sensitivity level is 0.997, which means 99.7% of the times the test is accurate in knowing that the person has HIV. All right. And specificity is 98.5%. So we're saying 98.5% times the test is accurate in telling that the person does not have HIV, which means 0.3% of the times the test fails to detect an HIV, and 1.5% of the times a person who doesn't have HIV, the test will end up showing that this person has HIV. Is this clear? And then it's also given to us that the probability of the population, the density the of HIV is 0.001. Means if I was to take, uh, say, how do we measure this? So the earlier two are measured by the test. How do you measure this probability of D 0.001? This is known from data, right? You say, okay, India's population is a billion people, right? And reported cases of HIV, whatever the number, all right, say a million, which means the probability of PD would be 0.001 in this case, right? So is this clear? How we kind of measure these values? So the PD is measured not through any test but through actual data, right? Through the data of population we know, count of population we know, and the count of cases that showed up. Whereas these two are measured using the tests. So this data is known to us. Now, what am I interested in? I'm interested in if the test showed up positive, all right? What is the probability that the person is actually belonging to the HIV set, right? Or the person actually has HIV. This is what I'm interested in. All right. So I'm saying I want to measure this, but I can't directly measure this, right? So I can use my formula to measure this value. Is this part clear, and how the practical usage of the part comes in, right? So I'm saying, so first thing is I'll measure the probability of the plus. What does it mean? Probability. So irrespective of the, so probability, the, if I was to keep performing my tests on the whole population, let's say, right? Then the probability of the test showing up positive is 0.0159, so on. How do I do that? I use the equation that we had seen earlier. So I use my equation, this one, right? This is the equation that I use. All right. I would want you to go back and solve this. I will anyways have, you'll have the PDF. But so is this clear? What I do? I say probability of the test showing up a positive. All right. Is probability of positive given that the patient is HIV into probability of HIV overall. Similarly, it will be probability of positive given that the patient doesn't have HIV into probability of not having HIV, right? That this value comes out to be 0.997 into 0.001 plus 0.015 into 0.999. I get this value. I get, so it's roughly about 1.5, or you can say 1.6%. All right. So roughly that is the value that I get. Similarly, I can measure P minus also if I need to. Okay. So it will be nothing but the difference of the two. So P minus is nothing but 1 minus P plus. All right. Now, so this is what I'm interested in, P of D, given that the test is positive. So I use my Bayes law, right, which is nothing but P of positive D, positive given D, and so on, right? Probability of D divided by probability of plus. And I get this value, which is 0.06238, which is roughly basically 6%, right? So what I'm saying now, I'm saying that if the test showed up as positive, so there is only 6% chance that the person actually has HIV. So it's, I mean, it sounds very practically different, right? Normally it says, suppose somebody goes for a test and the test shows up positive. The the probability is only 6%, not very high. There are still 94% chances that the person doesn't have HIV, even after the test showed up. That is based on these values, the sensitivity and specificity that we have here. Suppose these values are different, then the answer would have been higher. Is this part clear? Huh? So now I get 6% chance. Hmm? Okay, so now where is this interest? Okay, let's look at what's more interesting here. So one is called positive predictive value and another is called negative predictive value. What do you mean by positive predictive value? Given that the person, uh, given that the test has showed up positive, what is the actual case that the person is HIV, right? And similarly, given that the test has showed up negative, what is the reality that the person doesn't have HIV? So this is called the negative predictive value and this is the positive predictive value. Now these two values should be really high, right? Ideally they should be almost close to 1. Okay, that means your tests are really powerful. Are you getting this? So what we do is we introduce another parameter here called the diagnostic likelihood ratio, all right, which is kind of directly giving you these measures, of the effectiveness of the test, right? So I'm saying my DLR, so is the diagnostic likelihood ratio. DLR of a positive test is the ratio of two positive conditional probabilities. So one given the presence of the disease, another in the absence of the disease. So I'm saying, what is my DLR positive? It is the probability that I get a positive test given that the person has HIV. All right, divided by the probability that I get a positive given that the person doesn't have HIV. So what is happening? This is the correct value. This is the wrong value, right? This probability is wrong. This probability is giving me wrong results. This probability is giving me high results. So I'm taking a ratio of these two. This is a measure of my DLR. Okay. How do I use it? Let's see, where do I use it? Now what I'm doing is, so similarly I have a DLR for a negative value where I say probability of the uh, person not showing up with the disease given that actually he has HIV versus the reverse. Where is the so this was a case where there was actually the disease was there but it didn't show up, right? Tilde D is the case where the disease is absent and also it didn't show up, right? So I get both of these ratios. They're just some ratios, right? So I can also write down that DLR positive is nothing but sensitivity divided by 1 minus specificity, and so on. DLR is nothing but the reverse of this, 1 minus sensitivity or specificity. All right. Now understand this. Sensitivity and specificity are accuracy rates of the test. So they should be as close to 1 as possible. In our case, we saw it was 0.997 and 0.985, right? So now that is too less. I mean, it should be more close to 1 for our values to be better than 6%. We saw that the outcome is coming out to be 6%, right? 6% is not good enough. Hmm? So now what I can do is I can represent the value. I can represent my formula this way. I say probability that, so what I'm saying is this. So forget it looking at it mathematically. So what is the odds that any one of us has HIV? How can I tell that? What is the probability? Let's first look at what's the probability that any one of us has HIV. We have not gone through any test, right? Or any human being on the planet has HIV. Or let's say India, right? It will be given by P of D. Is this clear? Right? Yeah. So P of D, right? So from data, from P of D, we can say that. In which case, in this case, it is 0.1%. So without a person going through any test or anyone, we generalize it. We say, okay, so it is 0.1%, right? In our case here, is this part clear? Huh? Now, if I was to represent this as odds, basically odds is represented as happening or not happening, right? So I can say so one is probability is 0.01%, right? Sorry, yeah, probability is 0.001. Okay, so probability is 0.001. When I represent things in terms of odds, like say the matches, right? We say what are the odds of A winning versus B? It is done by the probability of, say, the event divided by the probability of the event not happening. Probability of the event happening divided by the probability of event not happening gives me the odds. Basically that's the definition of the odds. So what's the probability of pre-test odds? So I haven't gone through any test, right? So the pre-test odd will be probability of D divided by probability of tilde D, which in our case will be 0.001 divided by 0.999, okay, which is approximately equal to 0.001. Is this fine? So my pre-test odds are 0.001 divided by 0.999. Okay. Now what I want to know is what are my post-test odds, right? So what are my post-test odds? I've gone through the test and the test uh, has shown positive. All right. Then what are the odds? Or the test has shown negative. Then what are the odds? Is this clear? Huh? So is the test adding any value? So as I saw that initially the odds are 0.001. Now when I perform the test and the test ends up being positive, yeah, yeah, Utkarsh, shall I give you the mic rights? Ah, pre-test probability. So okay, yeah. Uh, Pre-test probability is PD. Okay, understand this. This is pre-test probability. This divided by this is pre-test odds. So odds are basically, terminology that has been devised maybe the better by the betting people, right? Because they, normal people, human beings, they don't understand probability, but they understand odds, right? So odds are basically just taking a ratio of these two. Got it? Huh? So that is the concept of odds, right? So I'm saying if this is my pre-test odds, what will be my post-test odds, right? So so now so the post-test odds will be, we already have the formula, right? And it so happens that if we do all the substitutions, okay, it comes out such that this value is nothing but DLR positive, right? So that is what we had measured. So DLR positive into the pre-test odds. So so in this case, it comes out to be 6 point, let's say 3%. All right, and all this divided by this, maybe it comes out a little more. Let's say it comes out to be 6.5%, right? So my post-test odds are 6.5%, provided the test turned out to be positive, whereas the pre-test odds were 0.1%, right? So so it is 60 times increased, right? If you look at it roughly, the increase is almost 60 times. So the value of n here, or DLR positive, tells me how many times. So I'm muting you, Utkarsh, because I think there was a sound from your laptop fans that was getting caught. Okay. All right. So do you see this? So this test has increased the chances by 60%, 60 times rather, not 60%. Is this clear or not? So the test turned out to be positive. The chances that a person has HIV is 60 times more than he had without the test, from the values that we had here, right? Roughly, I'm just saying roughly 60 times. Is this part clear or not, every one of you? So what I'm saying, the hypothesis of the disease is n times more supported by the test than the hypothesis of no disease, right? So the DLR positive gives me that value, comes out to be, say, maybe around 60. So it's a measure of the test, right? So I'm saying, what is the DLR positive for the test and the DLR minus for the test? So DLR positive, higher that value, more accurate the test is. Is this clear? Similarly, I can do post test odds of disease given the test is negative, right? Similarly, how my, so pre-test odds were, we already had that, right? 0.1%. So post test odds would be much lesser. So in this case, the DLR value will be a very small value, or rather 1 by DLR would be a large value. Is this clear? DLR minus. So have you understood the practical implication of the Bayes rule and the conditional probability? See, I didn't go through other details. I thought this is most important because this is what you will be using as such in some kind of analysis. So have you kind of understood this well? How's it? Sarvani has understood. What about the rest of you? Lavita, Debashri, Abhishek. Okay, Utkarsh has understood. Abhishek has understood. Okay. All right. Lavita has understood. Uh, yeah. You know, last time also there was some problem with the recording. I hope everything goes fine with the recording today. You know, what a rough idea about it, right? Okay. So I really want you to, whatever we did today, uh, or yesterday, right? These are the basis for, having a strong, firm foundation of uh, uh, analysis. Okay, make sure you really conceptually understand the PDF function, the conceptually you understand the CDF function. So not mathematically, you should kind of feel these functions, right? So then becomes really nice. Same with all any of this. So mathematics is easy to solve, at the same time easy to forget also. You can very easily get confused about the maths, but once this thing becomes a real solid concept in your head, then you won't forget, right? Then the math will just kind of support it. Is this fine? You have to understand, you have to ask questions, why this not this way, and so on, and that will make it more clear. Hmm? So uh, okay, right? So let me, what I'll do is I'll quickly go through the swirl part of the assignment, all right, to cover this up, and then we look at something else which is quite interesting again. Hmm? Uh, Let me change. Okay, so when you're running swirl, all right, there are no marks for the swirl assignment that is there, but it is very helpful in learning. Okay, so make sure you take care of one thing, that is you change your working directory to wherever you are installed swirl or something. There's this file has to be there. Basically, it's called cards.r, right? I don't know where I got it from. I think I downloaded it because the link was there or something. So, all right. So once I've done that, I've already installed swirl. I say library. Okay. So now I say swirl. Okay, you can also switch it, you can also start swirl on your laptops, right? So I'm starting the, oops, I started with the wrong one. I have to quit. No, I don't want to. How do I exit out of swirl? Hmm. Any idea how do you exit out of swirl other than having to shut down and restart the R? Let me just quit R and restart. Okay. Okay. Pressing zero. Oh, by function. Okay. Anyways, I've just restarted it. I'll just change working directory. Okay. So I say library swirl, the swirl, uh, shall we look at, so I'll just quickly look at both of these two once again, probability 1 and probability 2. Yeah, so quite a lot of the portion we had already covered in the last class, so I'll just quickly, very quickly graze through this. Okay, so how many outcomes are possible for a single die roll? We know this, right? We say okay, 6. Okay, and what's the probability of rolling a 2, right? So again, what's the probability of rolling an even number? 1 by 2, right? Keep writing. Okay, what's the probability of rolling two fours, right? So 1 by 36. Yeah, so what's the probability of rolling the same number two times in a row? Hmm? So you roll them some number, and then probability that you get the same number would be 1 by 6, right? Now consider the experiment of rolling two dice, one red and one green. Assume that the dice are fair and not loaded. How many distinct uh, outcomes are possible? This one again, some of you are new in the class today. How many distinct outcomes are possible if you were to roll two dice, one red and one green? I'm looking at the answer from you guys, especially those who were not there in the class yesterday. Okay. So Utkarsh, Lavita, Lavita was not there, na? Yesterday class. Oh, yesterday she was there. You had to leave midway. Yeah, 36, right? The outcomes are 36. Though, uh, uh, sorry. So the outcomes are 36, but 11 outputs are there. So understand that. Huh? So the outputs will be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, whereas the outcomes are 36. Okay. So if you're rolling two twice, what's the probability of rolling a 10? We have already seen this last time, right? So it'll be 3 by 36. What sum is the most likely when rolling two dice? We've already seen that also. Hmm? Okay. The probability of at least one of the two events A and B occurring is the same of their individual. Okay, this is the theory part. Okay. So which event represents expression represents the probability of rolling an even number or a number greater than 8. Okay. Solve this. I'll not. I think we can just. Do you want me to wait? So though we had done this yesterday also, just becomes a quick revision. Which expression represents the probability of rolling an even number or a number greater than 8? Yeah. Huh? So basically, you use probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B, right? And if you solve it yourself, you'll see the answer is the first option. Okay. Which of the following represents the probability of rolling a number greater than 10, right? So greater than 10 is 11 and 12. 11 you have two outcomes, 12 you have one outcome, right? So 3 by 36. He says, what is the probability of less than or equal to 10? Nothing but 1 minus 3 by 36. Okay. Okay. So now let's look at this is what we had not done yesterday. All right. So you have a deck of cards. So 50 tash ke patte hain. We have 52 cards, right? And you know how the deck looks like, right? So they've already created a matrix for the deck, right? Or a data frame. Says type D deck. Let's look at it. So this is how the deck looks like, right? So he's created 4 columns and named them as spades, hearts, diamonds, and clubs. And then the values are such that A of spades, 2 of spades, and so on. And then the row numbers. Is this fine? Huh? So this is what my data looks like. Okay. So when drawing a single card, how many outcomes are possible? So so I have a deck of cards, 52 cards. If I'm drawing a single card, 52 cards, right? How many outcomes are possible? How many outcomes are possible is 52 only, not 1 by 52. 1 by, yeah, right? 1 by 52 is the probability. So become very solid with the terminology. The moment you hear it, you should know what you have to, right? So okay, so then what is the probability of drawing a jack, right? Gulam आए कितना राघव राघव is there? At least I was good with cards. मुझे लगता है राघव भी अच्छा होगा. I know Sarvani, I got it. so so what's the probability of drawing a jack? So you have 4 jacks, right? So you have 4 by 52, right? So I have 1 by 13. Okay. So if you were dealt a hand of 5 cards, what's the probability of getting all the 5 of the same value? 0, right? Because at max 4 only can be there. So what's the probability of drawing a face card? Yeah, Debashri. फेस कार्ड कौन कौन सा होता है? जैक, क्वीन, किंग. ऑलराइट. So 3 into 12, right? So, Devashri, you had a question? Face card means either Jack or Queen or King, which means either 11, 12, or 13. Sorry, yeah, right? So the face card is, so you have, so three face cards per color into four, right? So 12, right? Divided by 52. Or you can say each deck is 13 cards. Out of that, you have three face cards. So you can straight away have 3 by 13. Wait. Uh, all right. So let's just look at what's the probability of drawing a jack. Now, probability of drawing a jack is what? 4 by 52 actually, right? In the whole deck, in the whole set of cards, there are 4 jacks, right? So it's actually 4 by 52, which comes out to be nothing but 1 by 13. So is this clear, Jack, Debashri? Huh? Similarly, Abhishek had a question. Abhishek, what's your question? What is not clear? So I should do everything in terms of 52, all right? So it will become more clear for you rather than. So what's the probability of drawing a face card? So how many face cards do I have? Per color, I have 3 into 4 colors divided by 52 total outcomes. So I get 12 by 52. All right. So this is clear. Now you're saying, okay, so you have already you draw a face card and you don't replace it back in the deck. So what's the probability that when you draw a second card, it will also be a face card? You already taken out one card, right? So what's the probability that is left? So it'll be, so here I have to, hmm, it'll be 12 minus 1 divided by 52 minus 1, right? Because one card is missing, right? Both from numerator and denominator, right? So the option number 1, right? So suppose you draw a face card and don't replace it in the deck. So what's the probability that when you draw a second card, it will also be a face card of the same suit? Same suit means same color, all right? So what will be this answer? So you, again same thing, but you're not replacing it in the deck. What will be the probability? Yeah, Utkarsh, correct. I'm just waiting for some other also to answer. Yeah, exactly. So I have 3 total cards minus 1, right? Because I've already drawn one. So I'm left with 2. And then 52 cards minus 1 because I've already drawn out one. So 51 is what I've left with. So that's what my answer becomes, 2 by 51. Okay. So let's start with the second part of the probability. So this was all right. Huh? So I'm making second selection. Okay. You've already seen this, right? If you had a ruler of infinite precision, would measuring the height of adults around the world be continuous or discrete? C or D? Where are the C and D options? Oh, okay, okay. All right. Yeah, continuous, right? So, Acha, what if the ruler was not of infinite precision? Ruler was of finite precision. Would you consider measuring the height of adults around the world be a continuous or discrete data? So this is simple and clear. This question is simple and clear. Now I say your ruler has finite precision. What would the answer then? For all purpose of analysis, you would want to use it as a continuous data, not discrete data. Because you would never have, if you were to draw the plot, it will always be a probability density function, right? You will not be able to give it as a probability mass function, kind of, right? Exactly. The population is so large, right? So the population is so huge that actually it will be used as a continuous variable. Anything biological typically should be measured as continuous. This is the point. Anything timeline wise and biological should be measured as a continuous variable. Is this fine? On the other hand, say if I'm drawing hands of cards, right, that is clearly discrete, right? Okay, so we've already gone through this. Okay, now this is interesting. So read this, right? So this is you have a coin toss, right? And okay, now let me just explain the concept of outcome and random variable. All right, from the outcome or the output. Say for example, coin toss. Outcomes are what? Heads and tails. They have nothing to do with 0, 1, -1, nothing. What am I doing? I am assigning. I'm saying, let me just do it here. Okay. I'm saying my heads should be equivalent to, let's say, 1, and my tails should be equivalent to -1. All right. So these are my outcomes, and this is my random variable. Instead of this, it could have been such that this is 1 and this is 0. So I can have anything defined as a random variable corresponding to the outcomes, especially when they're not numeric, right? If the outcomes are not numeric, in a lot of cases they'll be not numeric, right? There'll be some event that is happening. So this concept you should be clear of, right? Don't get confused that this is an outcome, whereas this is the variable associated with that outcome that I have mapped. Okay. Having said this, let's come back to this question. He says let x is equal to 0 represent a heads, all right, outcome, and x is equal to 1 represent a tails outcome. So in this scenario, it is actually heads is equal to 0, tails is equal to 1. All right. So if p is the probability of heads, right? So probability is associated with outcomes, right? So this has p probability. Clearly, this has 1 minus p probability, right? Hmm? P is the probability of heads. What is the which of the following two represents the probability mass function of the coin toss? So my coin is tossed. Which of these two will represent the PMF? Now, as such, let's not look at this. As such, the PMF is straightforward, right? PMF is straightforward. What is it? Value of 0 and value of 1, right? And this is half, and there's a point here and there's a point here, not a line, right? So my probability mass function will be something like this. Let me draw it with another, where this is half, right? So this is enough. Graphically, I can just represent it like this, where I can say 0 and 1. But how do I go about writing it as an equation? Especially if I have to use just single equation. Hmm? I can say x is equal to 0.5 for both 0 and 1. Or rather, no, I can say p for, no, so not half. In this case, it will be, let's say, so it will be something like this. This is, say, 1 minus p, all right? And let's say this is p. This is 0, this is 1, right? Let's say this is p. Okay, so this is what it is. I can also represent it as p for x is equal to 0 and 1 minus 1 minus p for x is equal to 1. But I don't want to do it this way. I want to do it in a one single equation. Have you got the question clear? So, so what I do, I replace x by 0 and I should get something like this. For x is equal to 0, the answer should be p, right? So if I say x is equal to 0, p raised to 1 into 1 as p raised to 0, this becomes 1, right? So one option 1 takes care of both the conditions, right? Is this clear? So basically what we do is, this is how you will tend to represent even your probability mass functions. They will not really be discrete. So they are discrete, but they're represented in a mathematical notation for ease of usability. Is this clear? Hmm? Okay. So he's taking on example. He's saying, okay, this is the probability that we had seen, right? The PMF. So we have already seen this. This represents, so same thing that I'm coming back to. We have already solved this actually, right? He's saying, so if you're throwing something randomly at this triangle, right? So what is the probability that will fit into the blue area? Okay. So that'll be, as we saw, it'll be the area under the curve, right? So this is the height that we saw. Okay, we've already done this. Uh, I will. I'm more interested in what will come after this. So we've already seen this as well, right? So he's talking about the CDF. So he has defined this function. I did that. Says PDF, my PDF. All right. So this is the function where it is defined as x by 2. All right. So now he's saying straight away use the integrate function. Okay. So survival function will be the reverse of that, right? So x square by 4, 1 minus x square by 4 gives me the survival function. Okay. So again, so he's talking about the percentile. What percentile is the 50th, right? So was the 50th percentile? We have already solved this. So what does that mean? Half of it. So now this is the question. Let's look at this. So I'm saying my percentile for this curve is at a value of 1.41. What does that mean? So if I was to throw something randomly at this triangle, right? Let's say I was to throw grains, all right? So I'm throwing sand grains. What, instead of kibble, consider it as sand grains, right? I'm just throwing them, all right? So now option 1, 2, 3, 4, which is the correct answer? All of it falls to the left of 1.41. That's the, what does this mean with respect to, again, you, so Sarvani, you're saying all of it should fall to the left of 1.41. Okay. Anyone else? I'm saying I'm throwing, so 1.41 represents my 50 percentile. Okay. And I'm throwing sand at this triangle, the bigger one. All right. From 0 to 2. Okay. So Sarvani, is the question clear to you guys? So I'm randomly throwing, so randomly something has to fall either here or there, and like that, say thousands of such grains are going to fall on this. How many of them will fall where? Half of them will fall somewhere, or all of them will fall somewhere? Utkarsh, Lavita, Raghav, is the question clear? Okay, so what will be the answer? Okay, I have this triangle, right? Physical triangle. Say I stick it on the wall, okay, the board as it is, and it is x-axis from 0 to 2, and then so I'm going to throw certain things at this, and everything has to fall within this only. It will not go outside. Okay. Now whatever falls on it, okay, it will fall spread out on this. If I'm saying my 50 percentile for this curve is at 1.41, which is something like this here, all right, a line here. What does that represent? What does that mean? Actually, I've already answered the question by explaining what I mean, right? So when I'm throwing it randomly, what will happen? It will be uniformly distributed throughout throughout the area, right? Throughout this region, throughout the whole big triangle. Now I'm saying 50 percentile means half of it has to fall on the left of that particular line and half of it will fall on the right of that particular line. Let me just explain it more clearly. Let's say what I'm saying is, say I was to throw something at this triangle, all right? I have to throw these things at this triangle, okay? Now I've thrown those things. Now the point is, I say this is my 50 percentile line, okay? So this 50 percentile line tells me that half of whatever I've thrown will be here and the other half will be here. Is this clear? So 50 percentile is kind of giving you the indication that half of the population, just another way of representing. So basically what you have to do is you have to convert a situation into a mathematical expression, and then once you've I mean or and that's how you'll be able to convert it into probability, right? Otherwise everything will be non-numeric as such. The reality situation is this, okay, this is what is there, I'm just doing this, what's happening, right? I have to convert it into a mathematical notation. So throwing stuff, and what is it equivalent to? Have you understood the question as well as the answer? So the answer here will be half of it falls on the left of 1.41. So this is okay. So what I want you to, so this you can go through. Let me go through another very interesting concept then now, right? So uh, now let's look at this concept of, I will first explain it theoretically and then we will look at an example and do it. Okay. So we're saying that for the purpose of uh, all these measurements in probability, my sample data, right, it has to have some properties, all right? So my whatever sample data I'm taking should have some properties. So, or the random variable that I'm pulling out of that sample data, right, has to have some properties. So now one is that what is the degree of dependence between the random variables? Say I toss a coin 20 times. So every time I'm tossing the coin, how much is the dependence of the coin this time from the previous times, right? Or say I'm, so this example is very obvious, the coin tossing. Let's say I want to measure the predict the poll results, right, for let's say uh, Delhi, right? So I want to predict the poll results for Delhi. Now how do I go about it? I have to do some kind of exit polls. So my exit polls is, first is I have to select people. Where do I should select such that they the degree of dependence between them is minimum, right? So that is why they'll be more random, right? So it's not that I've selected the members of the same family. If I select the members of the same family, what will happen? One influences the other, right? So I, or if I select the all the people in the one locality influences the other. So I have to kind of take care that there's a degree of dependence which is less. Second is the data heterogeneous or homogeneous? So how is the distribution of that uh, data? This may not be clear, we will look at it. Okay, so I'm saying I have two possibilities. One is that the data is independent of each other. Second is it is the distribution of the data is heterogeneous or homogeneous. So I have four possibilities, right? I can have uh, IID, right? That is, data is independent, all right, but independently distributed also, identically distributed, sorry, right? So which means homogeneous. And then I have data which is dependent and heterogeneously distributed. Okay, we will look at these are just concepts that I'm giving you right now. Okay, all right, so what does that mean actually? I'm saying that say I'm tossing the coin. Let's look at the coin toss example, right? So what is the coin toss example distribution? The distribution for the coin toss is what? Let's assume it's a fair coin, right? Let's assume it's a fair coin, which means the distribution is either, so random variables can be either 0 or 1, assuming that I have said, let's say say heads is equal to 1, tails is equal to -1, let's call it. Okay. uh, right, so I have this. So I say my tails is equal to -1, heads is equal to 1, and this has probability of half and this is probability of half. This is my distribution curve, right? Now this is my distribution curve. Now, so now I'm tossing the coin once, all right? So I get some output, either -1 or 1. I'm tossing the coin again. I get some output, -1 or 1. I'm tossing it again. I get the outputs. Now what is happening for each of these tosses? My distribution is identical, which means the initial probability of any of the values or any of the random variables is the same. Is this clear? The probability before I make the toss, or probability rather, is the same. So that is what I call by the identicalness of the distribution. My distribution is identical. First thing is clear to you? My distribution is identical. Second part is, how will the distribution be not identical? Let's say I have tweaked with the coin such that when I toss it, so here it is 0.5 and 0.5, right? Say if I tweak the coin, all right, I say that the second coin that I have is such that probability of getting, this is zero point 0.6 and this is zero point 0.4, all right? So I have a different distribution for the two coins. Is this part clear to you guys? So distribution here is different from the distribution here. We'll look at the same example, but tell me one thing. Let us take care of any of these two cases. Let's assume this. So first coin I used, and this was my distribution, 0.5 and 0.5. Okay. Second time I toss the coin, the distribution is zero point 0.6 and zero point 0.4. It's another coin, not the same coin. All right. Does the probability of getting a heads depend on what I got in the coin toss for the first time using the first coin? No, right? So the probability of getting a heads does not depend on what happened in the previous coin toss, even though the probability distribution is different. So that means they are independent. So this random variable will be independent of this random variable. So that is what we say, independence. And then second part is, we're saying we will normally work with data where the distribution is also identical. Is this clear? And that has certain specific properties. Such kind of data is called IID. All right, independent identically distributed data, random data. Is this clear to you? Voice is getting cut. Are you guys can't hear me? Is this the case with all of you? You sitting in the classroom or in your rooms? Sarvani, you can hear the voice. Utkarsh, can you hear the voice now or not? So, let me just try to chat. Who all can hear the voice? Okay, clear, right? Okay. Okay, right. So is this clear? Let's look at another example. Let's look at the um, die roll, right? In the die roll, so I have 1, 2, 3, 4, 5, 6, 1 by 6. This is for a fair die. All right. So I roll it once. The probability of getting a 4 in this case is not depend, or the probability of getting a 4 in the second case is not dependent on the first die roll, isn't it? So that's what we said when we say independent random variables. So that is independent random variables. Then identically distributed, say the second die roll is also having the same PMF. Is this clear? When the probability mass function is the same for both, that is called identically distributed. Is this part clear to you? So is IID clear to you? What is the uh, basically in statistics, when you kind of conceptualize something or when you get it to a mathematical level, you would be dealing with IIDs. But typically this will not be the case, right? Typically there'll be some dependencies, and then you'll say, okay, what is the correlation, right? So ideally the correlation has to be zero. But typically, say when you're pulling out people, etc., you say for example pole exit, right? Let's say the pole exit. So there is a correlation involved. So there is some dependency that is involved, but you can measure it, right, from your data. Say so this is a one statistical concept of IID. Now, what does this concept say? It's just this much: fair dial thrown many times in the sequence, right? So it is an IID, right? Because I'm using the same die, right? Even if it is a loaded die, will it still be IID? Tell me this. Indi- Full form of IID is this: independent and identically distributed. So two parameters: independent, so that the random variables are not dependent on each other, and then the distribution of that random variable is identical. So that is what an IID is. So we will normally, what we will assume is that samples are random and the variables are IID. Okay, this is what one strong assumption that we move with in statistics. Okay, and we have to kind of support it, and that this is the whole trick. Okay, what's a loaded die? Uh, Let us say I tweak the die in such a way, I create the weight of the die in such a way that the probability of the die becomes like this. So normal fair die is such that it will always get a 1 by 6 probability of anything, right? Here I'm saying the probability of 1 is, let's say, 1 by 5. Probability of 2 is 1 by 7. Probability of 3 is 1 by 8. Probability of 4 is 1 by 5, and so on. Got it? Such that the sum of all of this is 1. So this is a loaded die. I've tweaked with my die. What happens in gambling places, right? So the roulette are there, right? With the gamblers or the gambling machines sometimes are loaded. Sometimes they may not be exactly accurate, and the people who are making them work, they know how to deal with it. Okay, yeah, Utkarsh, you got a question? Identical, not identical, identically distributed. They are not identical, identically distributed. So ID is one word and I is another word. I is independent and then ID is identically. It means that, say, let us say this is my I. Okay, let us say I give a die to each of us, right? So 8 of us are there, each of us have a die, right? And now each of us have a die. What is the When can we say it is identically distributed? When each of our dies, and say, okay, now I'm saying I want to measure the experiment such that each of us roll the die, right? We will get some outputs, right? That will be my uh, outputs from the rolling of the die. Hmm? When can it be that every one of us got a uh, we were on the same footing? When can we say that we were on the same footing? When our dice have to be identical, right? What does that mean? That the distribution of the die should be identical, whether loaded or not loaded. So it means either all of our dice should have a distribution which is something like this, or all of our dice should have a fair distribution or whatever. So all the dice should have the same uh, probability mass function. That is what it means by the identically distributed. Is this clear now? So just assume I have a die which is giving me sixes more of the times, right? And you guys have a die which is fair distribution. So I have an advantage. On the other hand, all of us have the similar kind of die. then that is not an advantage. Got it? No? Hmm? So that is what I mean by IID. So is IID concept clear? Hmm? It's a very uh, key concept of statistics, but I'm not even explaining the whole thing. Uh, I'm just kind of giving you the definition of it rather. Hmm? But if, at least the definition should be clear. What does identical stand for? What does independent stand for? Right? Identical distribution. All of you are clear with the definitions? Okay, right? So now having said that, let's look at some nice example of IID. Now, there's something called a central limit theorem. I don't think it's there in the notes, but all I just want to, very quickly say it out. Basically, what is a central limit theorem? It says that if I have a IID random variables, all right, okay, and if I was to take so I have IIDs random variables, and I was to do my experiment many number of times. Let's say uh, I'm uh, say I'm tossing the coin 10 times. Okay, I'm tossing a coin 10 times. All right, so I'll get a sequence of heads or tails. Say let's say my sequence is something like this, right? So if there's a 0 represents tail and 1 represents heads. And if I take the mean of these values, I just take a straight away mean, right? Mean will vary between 0 and 1, right? Some value between 0 and 1 I'll get. And now I repeat this experiment large number of times. And each time I'm taking the mean. So whatever this mean is, if I was to plot this mean, it will be a normal distribution curve. Okay. Uh, so the mean, when I plot the mean of this, it will be a normal distribution curve. This is called central limit theorem, and I will actually show it to you with data. All right. So that's how it becomes a normal distribution curve. Okay, Utkarsh. Let's look at an example here then. Okay. Uh, ये कहाँ से शुरू हो गया? Let me just quit. So have you understood what it is? What is called a central limit theorem, right? And the central limit theorem is applicable for IIDs. Okay, but in fact, it is also applicable just for independent uh, variables. Does not require that the variables are identically distributed. We will look at an example for this. Mm, so what I do is, uh, you can see my screen, right? So what I'll do is I want to create a same example. I want to actually implement it. What I'll do is I'm going to do a coin toss, say 100 times. All right, and then I take a mean of that, and then I'll repeat this experiment say 1000 times. Okay, and then I have 1000 mean values. I'll plot the histogram of it, and I'll see what the histogram looks like, right? From based on the theory that I told you, what should the histogram look like? I told you some theory about CLT, right? Central limit theorem. What should the histogram look like? Should be normal distribution curve, right? So so let's see this. Okay, so what I'll do is, let me first create a I think R binom will do that for me. Okay, what does R binom do is, say my say 10, okay, size is 1, probability is 0.5. Do you see this? So this function takes care of it. So I've tossed the coin 10 times and I'm saying the probability of getting a value 1, right? So this is the size, don't bother about it. Just basically if I was to change it to 2, what will happen is the values will range between 0, 1 and 2. Correct? So that's what it is. Hmm? Instead of that, in my case, I say 1. All right. Is this fine? So 0, 1, 0, 1 is what I'm getting. So I have tossed the coin 10 times. I get the outputs like this. So notice that every time will be different. So I keep on executing it. I get different outputs. So it's effectively a random generation. Is this much clear? Right. So I'm tossing the coin. Now what I'm doing is I create a matrix. So okay, now so I can toss the coin 10 times or I can create R binomials and then I can split them into chunks of 10. So I keep on tossing the coins. For every 10, I take the average. So what I'll do is I say I create a matrix. I say matrix. So matrix will have some data. Let's say in my case, I want to have the data which is I want to toss the coin 100 times first of all right? And then I want to take 1000 times. I want to repeat it. All right. So this is my data. My data will be 1 lakh coin tosses, right? Out of that, I say I would create how many rows? So I create 1000 rows and 100 columns. All right. So I'm creating a matrix. So let me assign it to my MD. All right. So I'm saying my matrix data is this. All right. So if I was to look at what does MD look like, so it has 1000 rows and 100 columns, right? And then the value is either 0 or 1. Is this clear? Let's say look at head of MD. Are you getting what I've done? I created a matrix of random variables where there are 1000 rows and 100 columns. All right. And each of the values here is either 1 or 0, which is randomly given to us. Fair enough, right? Now what I'm doing is I'm saying, okay, let me take the mean of these values. So I can take the mean of one particular column, but I want to take the mean of each of the uh, sorry, rows, right? Not the column, the rows. So I want to take the mean of each of the rows. So how can I go about doing it? I think I can use the function apply. All right. So I say apply works straight over on a matrix, right? So my data is MD and then margins are rows, right? So I say 1. Okay. So that's the option of apply, right? So margin is row and then I say mean. Okay. And let me store it in my right? M mean, right? So now what I do is next is, so if I look at so I get some values. All right. 1000 values I will get. Is this correct? How many values will have? Where is basically the mean of each of the rows. This is my matrix, right? 100 columns, 1000 rows. And I'm taking the mean of each of the rows. How many values will the 1000, right? So I'll have 1000 values. Now what I'm doing is I'm plotting this. Okay. So my is already there with me. And then I say histogram of Okay, now what I'm doing is I'm kind of changing the bins. So I'm saying number of breaks is, let's say, 20. Isn't it amazing? Something closer to a curve kind of a thing you can see, a bell curve with the mean at around 0.5. So we had only ones and zeros, and that ones and zeros randomly distributed is giving me a bell curve, right? Giving me a normal distribution curve. Let's do this whole thing in one line. Okay. Uh, so this is my MD. Okay, what I'm doing is so that we can change it easily. All right. Uh, so let me straight away. The reason why I'm doing it in one line is so that we can. Uh, so I'm applying. So I'm creating a random variable data here. Okay. Margin one function mean. All right. So once I'm done with that, uh, I capture it in MD. All right. And then here I say hist of MD colon, let's say 30. Okay. So I'm getting this, right? So what I'll do is I'll change this now. What are the changes that I'm making? I'm, or rather, let's do a more interesting way to do it. Okay. I say NR is equal to 1000 and then NC is equal to 100. All right. And then I replace this by NC into NR. And similarly, here I can say NR and I can say NC. Is this fine? I get the same thing. Now I come back here and I change my values. I say, so I'm increase uh, number of columns will give me the summation that I'm doing, right? So let's uh, keep this as 1000 only. Number of times that I'm doing the experiment, I'm increasing it. So I'm making it 10 times, 10,000 times now. Let's look at the curve. It has become even more neat, right? Let me do it 1 lakh times. See the curve, right? Getting more and more closer to the bell curve. So instead of 30, let me do the binning as maybe 40. So are you getting it? So amazing, no? Looks so neat. Exactly the normal distribution curve that you would get. And this is happening from mathematics. From I mean, and not just mathematics. It is happening from data, and the data was only zeros and ones, right? Though mathematically, yes, this is very true. But for me, this is an amazing thing that actually we can see it also with data. For me to do this in Excel was much more complicated. I had done it in Excel, but takes a lot of time, whereas R kind of helps you to do it in single shot. Have you understood what I've done here? This basically is called the central limit theorem, right? That your data, which can be having any distribution, I keep on taking the mean of it and I plot that output. Exactly, it's awesome. I'll get a normal distribution curve. So basically, what we are saying here is that's why typically all these technical analysis and all for what is it for stock markets, the people who are dealing with fundamentals, they say, look, mathematics says that if you continue doing it for a long period of time, it has to get evened out, right? It has to get balanced out. So therefore they don't give value to it, but there are still people who do it. Okay. And I can't figure out where the difference is. Maybe it is the correlation part, because this assumes that IID is there, right? This works with IIT data. So is this clear to you? What we did? We did a random coin toss. Now instead of coin toss, I could have generated, what I could have done is, now let's look at this. I'm going to do another thing. So this is one. All right. So I'm making a change. Instead of binomial, let's say R norm. So I'm creating R norm. Okay. And so I'm creating normal variables. All right. With the standard deviation of one and the mean. Okay. Let's look at something more interesting here. Okay. So I'm doing this thing. Let's see what happens. Right. So what we can do now is uh, Wait, how can I find out the variance of this? Is there a function called variance in R? Basically, see, when we started off, our variance was 1, right? We used R norm, right? So R norm has a mean of 0 and a standard deviation of 1. When I take the mean of it and then plot it further, let's see what my it's still the bell curve, right? With a mean of 0. But what is the variance now? Will it be 1? Will it be different? Are you getting what my question is? Where is it? So MD is my final data, right? So my variance is 0.001 roughly, right? Let us look at what is my mean, right? Mean of MD is almost 0, right? And let us look at the original data. The original data was, uh, let me change it. So I'm just doing some mathematical proofs here for you. Okay. Uh, Taking it out, I'm saying dd, all right? And then I'm saying dd is equal to, I've done the same equation, I've just kind of introduced a, so look at this. Can you see this thing here? I'm saying my NR is 1 lakh, NC is equal to 100. Then I create a matrix which has that many rows and columns. Okay. And what I'm doing is I'm generating normal variables now. So standard normal variables, uh, not binomial variables, right? Let us look at the original data. So my original data, which is generated by R norm, what that is represented by DD, right? So what is my variance for DD? Oops. Oh, DD is a matrix, right? So, or let's say for each of the columns, okay? So variance for each of the rows, right? My data is taken row wise, right? So I say first row. So the variance is 1, all right? And what's my uh, mean? Mean is should be actually 0, right? That's how our R norm is, right? Are you understanding? So variance for the 100 values is 1. And let me increase this. What I'll do is I'm changing this data slightly. I'm making this 10,000. I'm making this 1,000. So I have, let me see let me show you what I'm doing. I'm saying I have 1,000 values, okay, in one experiment. And I'm doing a normal distribution, all right? normal distribution of random variables, which means I'll have a and standard normal, which means mean is equal to 0 and standard deviation is equal to 1. All right, let us look at that. So each of my curves will have that. Sorry, the data that I plot. So this is the equation that I used. So I pick up, I say mean of dd and the first row in it. Okay, so close to 0. It'll never be right. So variance is coming to close to 1. All right. Now what I do is I say, okay, I want to see what is the for the output, what's the answer. So my output is finally MD, right? I say what is the mean of MD and then variance of MD. If you notice, the variance of MD, so mean is close to 0 and the variance is something like 0.001, right? I can replace it by 0.001, right? Is it 0.001, which is nothing but 1 upon 1000, right? And how what is 1000 was the initial values here. So what I'm seeing is that if I have initial random variables which go something like this, when I apply central limit theorem on that, the data will become something like this. I apply central limit theorem on that, it will become more and more closer to the mean. Is this point clear to you? So what is happening in the central limit theorem? I would like you to play with these numbers and see, actually plot it and see how it works. So, or rather, what I should do is maybe I should plot it for you. What I'll do is hist of. Got it? No? You guys have got it? Understood what is happening here? Sarvani, you got it? What about the rest of you? Utkarsh, Lavita, Abhishek? So I'm just doing more maths than is even needed. But I thought this was really fun because once you start playing with this and you understood this, basically because basis of everything is standard normal distribution, right? And you've understood that, you kind of conceptually felt it, then it becomes easier for you to deal with anything. Yeah, so that was my whole idea. As such, it's not needed. This kind of maths may not be needed. Okay, but I mean, theoretically, you would have read all these things in your engineering or wherever. But here we are actually doing it and seeing that it's actually showing up the same way. Hmm? I thought it was interesting, therefore I'm doing it. Kind of digressing from the topic, but I still felt that what's more important is you have a feel for stats rather than just mathematics out of it. Yeah, I think that's it. That's where I want to stop. Uh, we will have a class tomorrow also, simply because we are running one day late, right? So we'll complete the expectations part of the other topic that is there. It'll be a small topic, and so that's it. Then we can take the quiz in the class itself. Yeah, so we'll do the quiz. So once you've gone through the two lectures that we have already done and tomorrow's lecture, you should be able to finish the quiz in the class in maybe 15 minutes time. This is fine. So we will have an in-class quiz. Okay, I think so. Okay, what about the rest of the guys? How do I mean? I really don't know. I've kind of done everything that I can do. I'm saying that I can start taking classes in the evening as well. So people who can come in the morning, they can come in the mornings, and then I can repeat the same lecture in the evening, provided I'm available. Like today, this week I'm not available because I have a course, right? Because say if they have to see my recordings, they might as well see the recordings directly from Coursera, right? Only thing is, okay, I would have simplified certain things, but the whole idea is to be in class because that kind of builds that rhythm. Who do you think you each of you can take responsibility for? So seven of you are there. Who all do you think you can take responsibility for to continue with the classes? Mehul and Vaibhav. Okay, Abhishek. Huh? Sure. You please give me feedback about the class also. No, it'd be nice. Like say for example today's class. How was it? Was it interesting? Was it slow? Was it fast? Was it that you actually learned something new, or was it that you already knew these things? Huh? I think I'll start taking that feedback every day, very honest feedback, so that I get an idea whether what I have to do. Right? We should experiment with evening classes. Yeah. So give me feedback on the class first, Abhishek. I mean, how was the class for you? Uh, do I need to improve certain things? I can't work on the or just your. It's like, say, attending the class. Would you want to continue attending this topic, assuming you didn't have any data science to learn? Nothing. Are you getting this? So, assuming it was not something that you had paid for, assuming just to understand that, okay, is it adding value to you? Like for me, when I'm teaching it, I feel rejuvenated. That's what's happening for me. Like in the morning I start, and once I'm done with it, I'm like thrilled. Wow, these are things that I kind of uh, not even taught, I kind of discussed. Okay, Devashri, right? So fine, so which means it's fine. Fine, so evening classes, let's experiment, huh? uh, we can do that from Monday. See, what I'm planning now is courses of 4 days each. Yeah, my art of living courses. Normally, I was taking 6 days. Typically, so Thursday, Friday, Saturday, Sunday will go there. So we can do our classes from Monday and Wednesday, right? So 2 days can be evening also, morning as well as evening, and then maybe Saturday can be or Friday can be morning, right? So something like that we can try out. Okay, so give me some more suggestions. All right, so Abhishek is taking responsibility for Mehul and Vaibhav, and Debushi will take responsibility for Shruti. Uh, I know Nitika prefers evening, yeah, but yeah, overall as a class, let's look at it. So there are outlier cases, a few of them, right? So overall data we should see. Okay, uh, who else takes responsibility for who else? Lavita, what about Dipankar? So I'm noting down, huh? Uh, Anmol and Supreet, Pakka Utkarsh. Anisha apparently said she's doing okay. Mol Supreet. Okay. Uh, Anisha was saying she's doing some morning sadhana and okay, Pratik, Raghav too. Anyways, Raghav, whose responsibility do you take? It will increase, no? I think same, Abhishek. We have to start experiment with the evening also. Maybe we'll keep morning as well as evening. Is that good enough? So those of you who prefer morning, I would give you the class in the mornings. And because see, the practical difficulties, I have to continue with my courses, all right? And my courses can happen either in the mornings. Earlier I was taking both morning and evening courses. Because of our data science thing, I'm focusing only on one, so that the team is my volunteers team is also organized like that. So what we will do is we will kind of I'll work on it such a way that I can give more time in the evenings as well. Or maybe it'll be such that evening, people who want it in the evenings, it can be Monday, Tuesday, Wednesday, and people who want it in the mornings can be Tuesday, Thursday, and Saturday, as we had planned earlier, right? So that way, kind of both get taken care. Okay, so please get more and more people to the class. It's so much more interesting, because interesting questions come when more people are there. Okay, you need to go now. Already 8:50 today. Bye, Abhishek. Jai Gurudev. Bye, Pratik. Pratik, you take responsibility for who all? Okay, Raghav, you said your group mates and Raghav. Okay. Okay, but we are already on Friday, right? So today's Friday. So this week not possible. Monday we will have a class in the evening, but tomorrow's class will be in the morning. Okay. So tomorrow please come in the morning, huh? And so that we can finish off this week stuff, and then we'll start the class from Monday in the evenings. Okay. So that'll take care of things. Okay, Pratik, please take care of Molly as well. Huh? No, but tell Anisha to come to the class. No, watching videos is not so much fun. Sitting in the class when everyone else is also there. Shall we start it that you guys start coming to the classroom? Would that be better, or that's too much of time consumption and wastage? I mean, even in the rooms, it's so good. No, just sit in the rooms in groups of 3 and 4 people, and you can just be in the rooms, and that's good. It saves time. At the same time, you are having still the class is going on. Rooms are better. Good. हाँ, perfect. So each of you should sit in their groups. Please wake up people, right? थोड़ा जिम्मेदारी ले लो, एक थोड़ा इनिशिएटिव ले लो यार. क्या होता है कि ज्यादा लोग आते हैं, एक इंटरेस्ट बना रहता है. मेरे को भी एक इंटरेस्ट होता है. अच्छा, सब लोग आएंगे, मैं आई स्पेंड टाइम टू प्रिपेयर. अच्छा लगता है मेरे को भी कुछ ना कुछ नया बनाना. जैसे ये वाला जो आज मैंने आई एक्सप्लेन्ड ऑल दिस, नो, आई एक्चुअली वर्कड ऑन दिस. मैंने पढ़ा, मैंने कहा अच्छा लेट मी डू इट यूजिंग आर, हाउ कैन आई डू इट. आई हैड डन इट अर्लियर विद एक्सेल, बट आई सॉल्व्ड इट सो दैट वी कैन डू इट इन द क्लास. No? So it's so much of a kick for me also to spend more time preparing for your class when more people are there. Even otherwise, even if less people are there, I'll still prepare. But it's so much more, nicer. तो करो एटलीस्ट. फर्स्ट ईयर वाले तुम लोग मिस नहीं करो. तुम लोग, बिकॉज व्हाट आई एम सीइंग इज डेटा साइंस अभी यूरोप में इट इज. आई सेंड यू एन आर्टिकल, फोर्ब्स का कल का ही आर्टिकल है कि यूएस में तो एकदम कमर्शियल लेवल पे आ ही रहा है. यूरोप में शुरू हो गया है. आफ्टर यूरोप इट माइट बी एपेक लाइक सिंगापुर एंड ऑल दीज प्लेसेस, राइट. एंड देन इट स्ट्रेट अवे हिट्स इंडिया. राइट, इंडिया मेनली बिकॉज चाहे कंपनीज डायरेक्टली नहीं यूज करें, दे विल यूज बिकॉज द बिजनेस इज कमिंग फ्रॉम यूएस एंड यूरोप, right? So by the time you guys are in your second year or you finish your first year and internship and all, you will see many opportunities coming up for you to do the projects. तो जितने तुम्हारे वाले 12 लोग हैं वो तो सब लोग जरूर आए, right? And actually it holds true for even the second yearites because अभी तक जॉब सीन में मतलब बोलते नहीं होंगे डायरेक्टली बिकॉज कमर्शियल लेवल पे आ रहा है. But by the time you pass out, the curve is such that it will be very fast, and you will actually be, you know, seeing yourself in this area. No, so ठीक है. See you tomorrow. Anything else? Okay, thank you so much, Sarvani. Bye, Sarvani. Jai Gurudev. Bye, Pratik. Jai Gurudev. उत्कर्ष कुछ बात करना है? ठीक है. चल, बाय. जय गुरुदेव.